I'm hoping someone else has already pre-explained principles and like fundamentals of what vacuums and pressures are will help compared to trying to read what I type out on YouTube. I haven't even read this before what I told you, but everything in here is pretty damn common and exact to what I've been saying. But the fundamentals of vacuum theory, and it's a box with molecules flying around in random directions, hitting the walls of their container. That would be pressure. And saying you got to understand the basic science of vacuums: low vacuum, medium vacuum, high vacuum, which, funny enough, that altitude chart I gave you earlier, that stems from you being like, oh, a pressure can't exist next to a vacuum. And the word vacuum is just a relative lower pressure compared to a higher pressure. And right here where you are now, standing wherever you are, the pressure of the gas of your feet is higher than the pressure of the gas of your head. So the gas of your head is a vacuum compared to your feet. And if you don't think that's enough of a vacuum, then go up to Mount Everest and go up to where like the highest altitude planes can fly, and the level of pressure up there is like a greater vacuum than most people get in their vacuum chambers. Like to get to where you have vacuums that are like vacuum uh, chambers are better than an example of like some realistic height you can even get to in our atmosphere. You need like these crazy, amazing industrial vacuums. It starts getting crazy expensive. So any video you watch of a vacuum chamber, you could just, there's an altitude you could just go to, and that that level of vacuum is up there. The ones that are exploding things and making foams get bigger and marshmallows and balloons pop, that exists just going up in the air. There's no boundary you go through. You go up to a vacuum just by going up. And this site does really good having pictures and explaining, which is just essentially the same thing. And the thing I think people don't like, because they like to say the word suck, a vacuum sucks, is that this explains that there's a flow, there's a crossover point in the number of molecules in a container for pressure and or vacuum, whatever way you want to think about it. Lack of pressure is a vacuum. That most of the motion of molecules can be dictated by running into other molecules, which is what we would probably call like normal pressures or high pressures. And then there's a point where hitting the walls of a container is more likely than hitting molecules. So that could be the one thing that becomes confusing in here, but it ends up saying about that you probably don't realize the scale of getting down to crazy vacuums, but it's if you took like a meter by meter container sealed and you want to get down to ultra low vacuum, you would have to make that container bigger than the entire volume of the Grand Canyon to get down to what an ultra low vacuum is. It's no small feat that's easy to imagine of increasing in this amount of nothingness compared to the amount of molecules. It's still giving examples of you probably don't realize how crazy pressure is and the number of molecules. The theory of kinetic theory of gases, the gas laws. Talking about, okay, this is the mean free path. This is a little chart showing that inside of whatever container you're set up, if it is this crossover point of these two lines, if it is more likely for molecules to run into molecules than it is for them to run into the container, then the flow of your molecules is dictated by hitting other molecules. So you get down low enough where you're at a point where the molecules are not more responsible for shoving the other molecules towards an opening where lower pressure exists. It becomes so sparse that they're flying around laser beam paths, have to randomly hit where they're going to exit. That's what this root mean path thing is about. Yeah, for this reason, at high and ultra-high vacuum, molecular collisions with the walls of the vessel dictate the pressure exerted by the gas on the walls of the vessel. So at a point, the only pressure, which pressure is the hitting of the molecules into the walls of the container, they are more likely to result from that from hitting one wall to the other wall than they are from hitting other molecules and then the walls being hit. And the very interesting part, where they have already available and better pictures for what I don't want to have to draw out. We're talking about temperature, changing the pressure of gas. The same amount of gas is in there. It's just you've slowed it down so much that it doesn't create pressure anymore, so a balloon shrinks. And then here's a picture when there's enough molecules and they're at the point where their motion is mostly dictated by shoving into each other and the friction involved with that. They tend to travel as a unit, and you would see like what would feel like pulling a set of molecules and having the others come along and get pulled with it, quote unquote, is what it appears to look like. And you get down low enough where it is much easier to realize that they're just little laser beams of particles flying around hitting the walls. They are always doing this, but at a point when there's enough of them, they're running into each other more than they're running into the walls. And it even gives the example, which I didn't even read this before I gave you this example of balls on a billiard table. When it's ultra high vacuum, the little opening is like the single outlet of a ultra high vacuum system trying to get as many molecules out as possible, because it's crazy hard to get an ultra high vacuum. When you get to the point that the molecules are not continually shoving into each other and looking like a handful of really small marbles that's almost like a liquid, they have to randomly fly into the hole. So it becomes this crazy game of chance with math, that you have a molecule that if you blew it up, it'd be like a baseball with 1,000 miles to the next molecule, and you're depending on it randomly running into the hole that's set to evacuate the particles out of there to make a vacuum. That's what has to happen. Let's talk about the flow, whether they're choked down and increases friction. So here's a good one. The viscous flow of molecules is just this point where you would see the molecules flow like you would classically think of a fluid. So the pump gets to removing one molecule out, instantly has the other molecules push on them. So even though the pushing of them is instant, it's still like a chain reaction of things that have to happen, and it doesn't leave instantly. If it left instantly, vacuum pumps, which the ultra high ones do, create like a perfect vacuum right outside of the container. They create the perfect vacuum right outside of the container, and eventually they have to get to the point in the hopes that the molecules randomly fly into the hole. This is not some made up mystery thing. There's companies that all they want is to make a perfect vacuum in a container. So they make a perfect vacuum right at a hole at the container, and your idea that a perfect vacuum right at a hole at a container instantly sucks everything out is not true. There's a whole industry of vacuum creating like systems where all they want is to get every molecule out of a vacuum. They'll never get every molecule out, but that's their biggest dream in the world. So they set up a perfect vacuum at a hole, and at a certain point, it's just math. They have to wait for random particles to be able to fly out into this hole, and then crazy things come into play when you put perfect vacuums at a hole to try to suck things out. You're doing random things like there's like a molecules of gas that gets stuck in like certain materials, and at vacuum, not even certain materials, almost every material has some random super tiny chance of math with there being heat that a molecule of it flies off. So there's like gases come out of things. Like if you make a vacuum chamber with stuff in it and you're not careful about the things you make the vacuum chamber out of, you will actually suck molecules out of the materials you made the vacuum chamber out of, and you will get gases that just get almost created. They're not created out of nothing, but they're coming from the things you expected them to stay in, and they fly out into gases, little separate particles. So it's like the smell of new plastic, like that type of thing. A vacuum chamber will take that out of materials at the point when you've set up a perfect vacuum at a hole, and you're hoping to play a time game of, I can wait long enough to randomly suck out gas molecules. But there's math involved where the goofiest set of qualities exist, where random molecules will fly out of your materials, and it's very, very hard to get a perfect vacuum. It's essentially impossible. So it has to wait for randomness. And the fusion is exactly describing this point. When you get to the point that molecules are more likely to go unimpeded, hit a wall, and then go unimpeded and hit the other wall, it is a game of nothing but randomness and math. A vacuum, a hole with a perfect vacuum outside of a container is not magic. Here's a picture. This side of a vacuum is a lack of something. A vacuum is not a thing, quote unquote. This side of the chamber having nothing in it before 5 molecules flew into it is a representation of a perfect vacuum. Perfect. There's absolutely nothing in there. It's a representation of imagination, but that is drawn as a perfect vacuum. There's nothing in it. A pinhole is put into the barrier that's separating the side that has gas. The gas is moving around because that's what gas does. It's molecules. When it's moving around, if it wasn't, it'd be absolute zero. And then before that point, it would fall down into liquid, solid, sublimate, whatever. If you slowed it down, they would not be flying around anymore. And on a place with gravity, or whatever you want to call what you think is a thing that's exactly like what gravity does, but it's not gravity, it's something else. The thing that pulls down matter. If you slowed them down, they wouldn't be flying around anymore and they would fall down to the bottom. Whether that's a solid or a liquid depends on the material properties, but as a gas, they're flying around with their energy that they have inside of them. Because when they hit, it's heat and pressure. When they hit something, they just bounce back, and it's not perfect, but the container they're in also has heat. Otherwise, that would be at absolute zero. So things that are at equilibrium with pressure inside of them is molecules with their natural motion that they have from their energy bouncing into each other, and they will just continue to do that. If the heat remains balanced in the system, the pressure will stay the same, the average movement of the molecules will stay the same, and they'll just be bouncing around like an endless animation of what this looks like frozen in time. They put little blurry lines like, oh, they're flying around. They would just do that forever. You put a small pinhole, there's a perfect vacuum on the other side. Every single molecule has to have its motion ending up pushing it into the hole. There is no, the hole is not pulling these through there. They just happen to have to fly through there. When there's a shit ton of molecules, they're right there just waiting. They're all shoving on each other. They're like tons of people shoved in the room where no one can move. As soon as an opening happens, it appears that you sucked a person out and more people had to get sucked towards you. But what is actually happening is everyone is pushing the person that's at the door. And then when it gets to this point, there's no other way to think about it. A vacuum, a hole is not a magician sitting there pointing at molecules and have every single one of them suck into there. You seem to have this thought that as soon as this hole is made, every single one of these molecules with their little motion blur tail is all instantly going to point to the hole and fly out. That makes no sense. That's not how it works. If that's how it works, no one that makes vacuum systems would have to worry about any of this, the details of how this works. It's complete nonsense. You would completely change the world if you were like, guess what? I know how to draw down a system where all the molecules just fly out of there. They would love you. This is hard to do. You get to a point where it's pure random math because the molecule has to fly exactly at the hole and make it through. Here you go. When you're past the point that the collisions are not more likely with other molecules, so that's that root mean path thing, the kinetic motion of the gas molecules dictates that molecules will pass through the hole when their path randomly directs them through it. Since at high vacuum, any hole or leak in a vacuum system is smaller than this distance, the distance that makes the cutoff point between molecules where they hit each other, where it makes that less likely than hitting the walls, it says the gas will not flow through the hole in an ordered group motion. Over time, this random motion causes some particles to eventually pass through the hole. A hole to a vacuum does not instantly magically suck out gas. There's still a rate. The size of the hole and the making of the gas molecule's pressure dictates a certain amount of flow. It's not just some magical... If you put a pressure chamber in space and you poked a pinhole in it, it doesn't just magically all the gas gets sucked out of there. Like if you had to zoom in what you would think is happening at the microscopic level, if you think that's legitimately what's happening, you would have to draw all of the dots. As soon as a hole is made, they instantly change their direction and just go towards the hole magically. Magically. You keep saying, I realize a vacuum is actually pressure, high pressure going to low pressure. Apparently you don't, because you can't. Making a hole does not magically move molecules. Like, the molecules are already moving and they just happen to flow through that hole. You, you have two of your own opinions make no sense next to each other. That's the majority of what I wanted to show you. Yeah. If I don't know how you could possibly make sense of what you're saying. It it just it defies your own logic. I don't know how you could think of your own thinking of this and say, yes, high pressure is actually pushing gas into the low pressure, but then you think a vacuum is magical and just makes everything instantly get sucked out of a pressurized container just because it's a very, very good vacuum. Like, it makes no sense. The people that make vacuum systems have small leaks, and their vacuums, the whatever system is made that has the greatest vacuum ever made known to man, has small leaks or small pressure going into the vessel that continuously fights it. There's an equilibrium point where they can't do anymore. And that same thing happens whether you're in space or any other low pressure, or any difference of two pressures is the same. It's a relative thing. A high pressure next to a low pressure is the same. Just shift the two numbers up and down. That's a difference of pressure that dictates the same math and the same physics involved. There's nothing magical about a hole to a vacuum. It's not a magical wizard sucker of particles. You say, I didn't say a vacuum sucks anything. And then you say it gets sucked when it's a pinhole is to a vacuum. You're saying the exact same thing. You're like, I'm not saying this, I'm saying this. And those two things you're saying are the exact same thing. A vacuum doesn't suck, but it's sucked from a vacuum. Like, what are you talking about? It makes no sense.